Hi everyone. This is the follow-up video that I just spoke about in the previous video, where I said we would do a little bit more with algebraically seeing linear and exponential functions. So hopefully this will be a somewhat quick video. We're just going to go through 8 different examples. So there's 1 through 8 here, but I'm just going to show you 1 through 1, 2, 3, 5, 6, and 7 apparently is what I'm going to show you on this screen. So if you're taking notes, go ahead and write down each of these 6 functions that you can currently see. And for each of these functions, we are going to list what is the initial value, is this function increasing or decreasing, and then find the rate of change. Now, if it's an exponential function, we're also going to list the factor so that we can see the connection between the factor and the rate of change. Okay, so pause your video now and go ahead and practice these 6 problems that you can currently see. Okay, while you are practicing, if you just came back, I'm gonna make my screen a little bit bigger and pull a whiteboard over it just in case I want to draw some stuff to help us understand what's going on, especially with the exponential functions. Okay, so let me see if I can move this over a little bit. Okay. All right, so for number 1, this is an exponential function. The initial value is 50. This is a decreasing function because this factor here is less than 1. So if I'm multiplying by a number that is less than 1, then I'm going to start with a value of 50, and then the next value should be less than 50 because I'm multiplying that by 0.4. And then the value after that will be less than that. So this is a decreasing function. Sometimes we also say that that's decaying, because it's describing exponential growth or decay. So that's how we talk about that. We say this is a decaying exponential function. The factor here is 0.4 or 40%. So you could write that as 40%. And if the factor, I'm going to draw on the whiteboard, that's why I thought this might be useful. If the factor is 40%, then that means that if you had a starting amount of 100%, and now you're down to 40%, then what you must have just lost is 60%, right? So this is a decrease down by 60%. And the 40% is the factor. That's what we go down to. So there you go. Now you can hopefully see the connection back to our percent lessons. And you can see that that would make this rate of change 60%. And we got it by doing 100% minus 40%. So I draw these kinds of little rectangular diagrams all the time just to help solidify my knowledge of how these are connected. So let's look at number 2. The initial value here is 27. This function is increasing. Why? Because the factor here is bigger than 1, because I'm multiplying repeatedly by a number that's bigger than 1. So this is growing exponentially. The factor itself is 1.03, which is the same thing as 103%. And if you are now at 103%, so let's put in a different color. Let's put an example of what's happening here. So if you increased to 103%, and you always start at 100, then what did you just add on? You must have just added on 3%. So that must be an increase by 3%. So that is your rate of change there. It should be 3%. All right, notice that I'm only dealing with percents when I have exponential functions. So when we do these linear examples, you won't have any percents. So for number 3, the initial value is 8. This is increasing because the factor 3 here is bigger than 1. So you're multiplying by a number that's bigger than 1. The factor itself is 3 or 300%. And if you know that the factor is 300%, then what is the rate? Well, since you always start with 100% and now your final percentage is 300, then your rate must have been 200%. If you add 100 plus 200, that'll give you the final factor of 300%. So this is a very rapidly increasing function. We usually say that this rate here is tripling, right? You have if you start with 8 people, or whatever it is that you're modeling, then every iteration you are tripling the number of people. So you started with 8, then the next iteration you'll have 24, and the next iteration you'll have 72, and you'll keep tripling. Let's look at number 5. So these are lines now. So the initial value here is 7. It's always the y-intercept. It's the thing not multiplying by the x. This is an increasing function because 2 is positive. 2 is greater than 0. Or you can just say because 2 is positive. If you want to solidify your notes here and make them really full, you should say that number 1 is decreasing because the factor is less than 1. And then the rate of change for lines is the same thing as the slope. So those are synonyms. So the slope here is 2. Not 2x, just 2. And no percent. For number 6, the initial value here is 5. This is decreasing because -3 is less than 0. In other words, because that's a negative, then this is a decreasing function. And the rate of change is -3. And then for number 7, the initial value is -10. This function is not increasing or decreasing because I don't see a slope here. So if you want, you could adjust this to say plus 0x. That way you can see the slope. So the slope is 0. So that means this is neither increasing or decreasing. And the rate of change is 0 because the function is not going up or down. Okay, so in other words, that means that this would be a horizontal line. It wouldn't be going up or down because the slope is 0. The rate of change is 0. Let's try these last 2 examples. So pause your video now and try those if you haven't already done so. Okay, and so for the exponential function, the initial value here, it's actually right there, even though it's not written, there's a 1 there, right? Because 1 times anything is still itself. So the initial value in this case is 1. This is an increasing function because 4/3 is greater than 1. So you're multiplying by a number that's bigger than 1. So this is increasing. The factor is 4/3, or if you want to write that as a decimal, that's approximately, let's change that, approximately 1.33, which is 133% roughly. And that would make the rate of change equal to 1/3 or 33% approximately. Let me put approximate because it's not exact. Okay. And again, this is increasing. So if this were a real life problem, you would say that the rate is increasing by 33% every x variable, whatever your x unit is measured in. Then this last one, number 8, the initial value here, I don't see a constant, so I could just write +0 for my I to help me see the mx plus b structure. So the initial value is 0 because there isn't one. This is increasing because 4/3 is positive, because 4/3 is bigger than 0. It's a positive number. And the rate of change is just 4/3, exactly what you see there. So no work needed to be done. Okay, so now we've done more practice problems algebraically that will hopefully really round out your knowledge of lines and exponential functions. So you've seen examples where the slope might be missing, it might be 0. You've seen examples where the initial value might be 0. If you're dealing with an exponential function, the initial value, if it's missing, it's always 1. It's not 0. If you start with 0 and it's an exponential function, you will always have 0 because say you start with 0 and your factor is 2, then you're doing 0 times 2, and then times 2 again, and then times 2 again, and you're just going to keep getting 0. So you can never have 0 for the initial value or for the factor or the rate if you're dealing with an exponential function. If so, it wouldn't be an exponential function because it would just be 0 the whole time. You can have those things for linear functions, and what you would see graphically is if you had an initial value of 0, but a positive slope, then this line would be increasing and it would go through the origin. That should look like it goes through the origin, not a great graph there. And if you had a line that had a slope of 0, which means it's not increasing or decreasing, depending on where the initial value is, it would just be a horizontal line. So here's a slope of 0, and then here is a y-intercept of 0 when we're talking about mx plus b. Okay. All right. So now you have a lot of knowledge of linear and exponential functions, and you have enough to start recognizing when you see these types of functions in your everyday lives. So when you see those patterns, when you see something adding or subtracting by the same amount, that would be a linear function. When you see something multiplying or dividing by the same amount, that would be an exponential function. There are many other functions out there, but we're only going to talk about those two in this course.